Okay, so in this booster class we're going to be doing a bit of work on shapes. We're going to start by talking about electron pair repulsion theory. We'll go through a few examples of some shapes of molecules and apply them, and then we'll finish off with an exam style question. So the whole of shapes is based on this theory called electron pair repulsion theory. So the idea is that electrons tend to exist in pairs, either as a bonding pair, that means they're in a chemical bond, usually a covalent bond with shapes, or a lone pair, so that's a pair of electrons that is not in a covalent bond. So you've only really got two choices, bonding pairs and lone pairs. And electron pair repulsion theory states two things. The first is that electron pairs will repel as far as possible. And notice that that's all electron pairs, not bonding pairs, not lone pairs, all of them. So both bonding and lone. So let's go through, what do we mean by that when we say electron pairs repel as far as possible? So let's say I have an atom, an element A, and that is bonded to 3 atoms of element B. Now, using my high-tech equipment here, I'm going to use pens to represent that covalent bond. So have a little think in your head, what actually is the covalent bond? So what is this pen actually representing? So it's representing a shared pair of electrons. This is the bonding pair right here. Now, let's say my atom A was bonded to 3 molecules of atom B, if I can fit them all on, just about. What's going to happen is these 3 bonding pairs of electrons, they're all going to repel each other, and so they're going to spread out by the maximum amount possible. So here will be a circle divided by 3, so 360 divided by 3. This will be a 120 degree bond angle, 120, 120. Now if I was to take this element here, or this bonding pair of electrons, and push it down here, this would then repel that pair of electrons, and they would get repelled over here. But then this bonding pair would repel that bonding pair, and that would get repelled up there. So that's what we mean when we say all electron pairs repel as far as possible. So that's that first statement. And then also, the second statement of electron pair repulsion theory is that lone pairs repel more than bonding pairs. They're more repulsive. Imagine that they're dead ugly, right? They're dead repulsive. They repel everything. So, going back to our example from earlier, here's our 3 bonding pairs. And there's nothing special about the red pen, I just only had 2 black pens. Here's our 3 bonding pairs of electrons. If I was to replace this top bonding pair with a lone pair, I'll just use 2 little circles, because that lone pair is more repulsive, it will squish these bonding pairs together a little bit more, because they're being repelled away from the lone pair. And very roughly speaking, each lone pair will push the remaining bonding pairs 2.5 degrees closer. So this bond angle will not be 120 now, it will be roughly 120 minus 2.5. So what's that, 117.5 degrees-ish. Okay, if I had a second lone pair, so if I had another lone pair here, well, that would push it even closer together, because now you get more repulsion. Okay, so that's electron pair repulsion theory. This is something you need to have on a flashcard and you need to boot camp. Okay, this is going to be important when we come to that exam question at the end. Okay, so In a second, we're going to look at some examples of some shapes. I'm going to get you to try and figure out what shape they are. In order to figure out the shape of a molecule, all you need to do is count the number of bonding pairs, count the number of lone pairs, and then play snapsy with whichever shape has that combination. For example, if you figure out your central atom has 3 bonding pairs and 1 lone pair, well, that combination gives a pyramidal shape. So stop the video now and take as long as you need to take to boot camp those combinations. They're all in the textbook under the shapes chapter, so you can get them all from there. Just start. You won't be able to do shapes until you've done this. This is the linchpin to shapes. So stop, memorize those combinations, and whilst you're at it, I would also memorize the bond angles that the shapes have as well. Okay, so that's a little bit of grunt work on your behalf. You just have to put the hour, well, it won't take an hour, but I would do 10 minutes, 15 minutes now. Tomorrow, go over it again for another 10 minutes. In a week's time, go over it again for another 10 or 15 minutes, and then it'll stick. Yeah, do some boot camping. So, stop the video. Welcome back. Hopefully you now know all your combinations. Here's some examples. What I'd like to do is, again, stop the video, try it on your own, try and figure out what shape they will be, and then I'll go through and show you how I do it. Welcome back again. So here's how I do it. First of all, I'd figure out how many bonding pairs and lone pairs the central atom has. Now, one way you can do that is to draw a dot and cross diagram. That'll tell you the number of bonding and lone pairs, but sometimes that can take a little bit of time. That's not a quick method to draw a dot and cross. So you can do that if you like, but as an alternative, quicker method, you can just use a periodic table. So here's how I'm going to know this. So first of all, figure out how many electrons your central atom has in its outer shell. So phosphorus has 1, 2, 3, 4, 5 electrons in its outer shell. So you literally just count across on the periodic table, ignoring the D block. So ignoring that, count across, 1, 2, 3, 4, 5. Okay, it's got 5 electrons in its outer shell. Each hydrogen will make 1 bond, right? Hydrogen only makes 1 bond. And in a bond, the phosphorus will be sharing 1 of its electrons per bond. Yeah, in a covalent bond, each element shares 1 of its electrons. So phosphorus starts with 5 electrons. As it's making 1 bond to each of the 3 hydrogens, and I'll be careful which of my fingers I leave up now, that will leave 2 electrons left over. So phosphorus has 2 electrons that are not in a bonding pair. Well, that must be a lone pair then. So my phosphorus has 3 bonding pairs, and then it has 2 electrons left over, because it has 5 in total, to leave 1 lone pair. As you've memorised your combinations, you should know that 3 bonding pairs and 1 lone pair, that is pyramidal. So if I wanted to draw this out, I'd have something that looked like this. And again, you just got to memorize what these shapes look like. If you've got some molymods, actually making that shape with the molymod and being able to picture it visually, that's really good. That'll really help you if you do that, because then you can see it in 3D. Let's try another one then. So silicon fluoride. So silicon has, being the central atom, 1, 2, 3, 4 electrons in the outer shell. Fluorine makes 1 bond, and there's 4 fluorines. So that's going to use up all 4 of silicon's outer shell electrons. That leaves none left over for lone pairs, so we have 4 bonding pairs and 0 lone pairs. As I've memorised my combinations, I know that is tetrahedral. So that'll look like this. That's a terrible bond, but you know what I'm trying to do? Here we go. Okay. Now what I did there is I knew that fluorine only made one bond, and I knew that hydrogen only made one bond. If you're not sure how many bonds elements tend to make, you can get that from the periodic table. So your noble gases make 0 bonds, your halogens tend to make 1, oxygen and sulfur, etc. tend to make 2, nitrogen and phosphorus tend to make 3 and 4. Now there are some exceptions to those rules, but most of the time this will be how many bonds things make, and then hydrogen makes 1. So you can just get it again by looking at the periodic table. You can get loads of stuff from the periodic table. And then it's a bit of a trickier one. We have our carbon dioxide here. So carbon, again, let's get our periodic table out. Carbon has 1, 2, 3, 4 electrons in the outer shell. Now oxygen makes 2 bonds, but there's 2 oxygens. So that's a total of 4 bonds. So again, carbon is having all of its electrons used up. What we're going to get though, I draw it out, is not 4 single bonds, we're going to get 2 double bonds. Now, when we've got double bonds, we shouldn't be talking about bonding pairs, because that can get confusing. Technically, there's 4 bonding pairs. But can you see that it's different to tetrahedral, because we don't have 4 single bonds, we have 2 double. So what we would say instead is 2 bonding regions. Okay, and then 0 lone pairs. So when you've got double or triple bonds, it's best not to talk about bonding pairs, but to instead talk about bonding regions. And again, if you've memorized your shapes, you'll know that that gives you a linear shape. Okay, so with double and triple bonds, don't think about the number of bonding pairs, think about the number of bonding regions. But other than that, it's exactly the same method. Okay, so let's wrap up with a very, very, very common exam question. So part A would be what shape does water have and what's the bond angle? And then part B is explain why water has that shape. So again, pause the video, have a go at it yourself. Once you've had a go, press play and I'll go through the answer. Welcome back. So whenever you're explaining any shape of a molecule, you only need to do 2 things. First of all, state the number of bonding and lone pairs. So on water, oxygen has 6 electrons in its outer shell, is using 2 of them to bond with the hydrogens, so that leaves you 2 lone pairs. So I would say the oxygen has 2 bonding pairs and 2 lone pairs. That gets you a mark. And then all you need to do after that is state electron pair repulsion theory. That's what we went through at the very start of the lesson. I'm just going to flick that up again. So you literally just copy that out. So your answer, fold this over, your answer is state the number of bonding and lone pairs that that particular central atom has, and then just state electron pair repulsion theory, and that gets you the 2nd mark. Okay, and that's it. So you're literally just regurgitating those same 2 sentences every time. The only thing you need to change about this answer is the number of bonding and lone pairs specific to the question. Okay, so again, as a model answer, I would get down state bonding and lone pairs, and then I would write those 2 sentences down, and that would make a really good flashcard for how to explain the shape of a molecule, because it is an incredibly common exam question. Thank you very much. I'll catch you in a bit.